The more we study the laws of nature, the more we see all kinds of things happening around us that are consistent with those laws, and we are now, at this point, going to investigate a feature of nature that is all-pervasive. Everywhere we look or don't look, we see or don't see its phenomena, but it's occurring. And we see it a lot, actually, also. And it is the phenomena known as waves, which travel through different mediums, different speeds, and have different characteristic properties. And we're going to investigate some of those things. So, the properties of waves. Vibrations that occur in nature, typically of a periodic nature, that are occurring everywhere. And one difference we see between types of motion, if we throw an object back and forth, we cause matter to transfer back and forth between us. But a wave is a disturbance in matter. A wave is a disturbance in matter. They don't so much cause the matter to travel, but they disturb the matter, and that disturbance propagates or moves. So the waves actually are moving energy. They're not moving matter itself. So that's the first key feature. There's a lot of other things that will become more clear and hopefully demonstrated as we go. So some of those things are that they reflect. You know, if you have a wave hitting a wall, it might bounce back. If you cause a wave to be initiated on a string, okay, say a guitar string, you flick that string, you displace it, and it travels along the string and hits the end of the location where it's attached to, it'll bounce back, whether you see it or not. All right, so they bounce or reflect. Waves also refract, which means they can bend as a result of a speed change. In fact, that's how your glasses work. That's how the cornean lens of your eye works. It bends waves so that it basically changes the speed so that they bend, and you can focus light where you want. All right, also waves diffract, and that's a bending around corners, or if you have a little opening in a water wave, for a water wave, it will, instead of just going straight through the opening, after it goes through the opening, it spreads out. These things are best visualized. So we're just listing them right now. Waves interfere as well. So if two waves interfere with each other, they may add or subtract their amplitudes, become bigger or smaller as they interfere with each other. And there's a lot of reasons for studying waves, and in brief, communications is a big one. All forms of communication almost that we experience involve waves. For instance, hearing. To hear my voice, there's sound waves being produced in the medium of air, typically. In fact, even as you're listening to it on your electronic device here, there's a speaker that's vibrating the air and causing a pressure variation, which is a wave that travels to your ear and vibrates your eardrum, etc. Then there's seeing. That's important too, isn't it? Of course. And that's done by light waves. We also have TV, radio. It sounds a little old-fashioned, I suppose, to say TV and radio, but nevertheless, your smartphone is basically a radio, and it communicates, whether it's text or voice, by electromagnetic waves. Keep in mind, as we'll see, electromagnetic waves is the general term, actually, for light waves. So even though I'm saying seen is light, that's visible light, TV and radio are also electromagnetic waves. I probably should say visible light is electromagnetic waves, because I'm listing it here. And the various wavelengths determine basically the function of the electromagnetic waves. But that's not the purpose of the topic right now. So what is a wave? It's a disturbance, as I already said. And that disturbance travels along something. The thing it travels along, you know, it's not moving this thing in the direction of the wave motion. That was a little confusing. The wave, the direction that the wave moves is not the direction it disturbs the object it's moving through. Okay, that'll become clear. The thing it's moving through is called the medium. The medium is disturbed, but it's disturbed in a way that's different than the way the wave travels. And that medium is often water. It can be air. It can be gas out in the cosmos. It can be the Earth itself. It can be a railroad iron beam. It can be a board. It can be a lot of things. All right. So now I want to investigate the various types of waves, and they can easily be categorized. The basics, we have transverse, and it's really easy to understand what that is. It's just simply a wave where the medium, the thing it's moving through, moves in a direction that's perpendicular to the wave motion itself. All right, so here's this little picture, and this might look like a water wave. I just basically drew a sine wave here because that's typically the shape that it takes, whether you see it or not. Ocean waves are similar to this, not necessarily quite exactly like this. But a transverse wave is easiest to identify the various physical properties of the wave, namely how we define it. We have something called the crest. So if you think of this as a water wave, here's the equilibrium level, and the crest is higher. It's where the medium is disturbed, and it's disturbed upward. Then, of course, at the furthest downward, the furthest point underneath the equilibrium is the trough. The height of the crest itself is known as the amplitude. We encountered that in simple harmonic motion, symbol A. And we have the wavelength. The wavelength is simply the point, wherever you're starting, it's the place where it repeats itself again. See, at this point, it's repeating what's going on here precisely. And you can start anywhere you want. I mean, I could have started the wavelength here, and then it would just go to about there, the same place again. Okay, and lambda is the symbol for wavelength. So there is a trough to trough, equilibrium. So equilibrium to equilibrium, trough to trough, or any other thing that you want to, any place you want to start. And the motion is to the right here. This whole disturbance is moving. The disturbance is moving the medium, just like I'm showing here, up and down, but that disturbance then travels, even though the medium doesn't travel. The disturbance does. Very important distinction. So the crest might be a little bit obvious from what we've said. The top of wave, trough is the bottom of the wave. The wavelength, lambda, includes a crest and a trough. The amplitude A equals the maximum displacement from the equilibrium. So just clearly defining those things. Now we have a term called the frequency. We've all heard of the word frequency. It's just the number of waves that happen in a given amount of time. So typically the time unit is seconds. It doesn't have to be. But number of waves per second. It's also number of cycles. The number of cycles that this goes through from crest to trough. Well, equilibrium to the second equilibrium after that, where it repeats itself. That's a cycle. One wavelength is progressing through one cycle. All right. And that unit for frequency is hertz. Cycles per second. Hz is the symbol. Now, how about the period? The period is simply the time it takes for one wave to occur. So it's how many seconds per wave. And if you notice the relationship between frequency, waves per second, and periods, seconds per wave, yes, they're inverses. 1 over f. All right. Then we have longitudinal waves. And longitudinal waves are different than transverse waves, mainly because of the way in which the medium is disturbed. Instead of being perpendicular, it's parallel to the direction the wave travels. Same direction. So let's check this out. This doesn't quite look like this. I made a triangular wave here, but we have a compression region here. Simply where the medium itself is compressed, and therefore it's more dense, actually. Increase the density. So this is easiest to demonstrate with like a slinky, a spring, where you can see the turns of the slinky closer together. Followed by an expanded region, shown that over here, called a rarefaction. It's a region of less density. And so as this travels, you have these continuous compression and rarefactions that follow each other. So the wavelength is where it just repeats itself again. So it's the same idea as before with transverse. Just might be a little bit harder to see here, but it's this same idea. And so the motion is in the same direction as those compressions and rarefactions. If you notice this compression here, it's as this compression moves through, in front of the compression, it's almost like to compress this, it had to draw some of the medium toward itself, and it does the same thing back here. So in front and behind, it's expanded. The medium is expanded. It's rarefacted. It's less dense. And that propagates through the medium. And finally, surface waves. Really, surface waves are just a combination of the two. They're made of both transverse and longitudinal components. So that happens, especially because though the vibrations of the waves occur at the boundary of two media. Like, for instance, the water is in contact with the shore, the bottom of the lake or whatever it is, the ocean, and they interact with each other. So what happens is that you can see the transverse part of this. So there's the up and down, but also the water itself is moving. If you ever, obviously, you've all seen how waves coming into the shore will break. You know, there's kind of like, there's an actual motion of the water in the direction of the wave itself. As it approaches shore, the speed of the wave on top is greater than on the bottom. So there's a rolling effect. So if you go up and down and then forward at the same time, you get this rolling effect. It's shown as circles here, but in general it's elliptical. So you have elliptical motion of the particles of the medium itself, namely the water. And the wave is moving in the same direction. And so, to summarize, we have the primary wave types and just kind of a little picture. So here's transverse, and you put a disturbance near, the motion is to the right. And this is what the particles are doing. Up, down, up, down, up, down, all along here. And they have different displacements at different parts of this wave pulse. I'm going to call this a pulse now instead of a wave, but they're kind of the same thing. Longitudinal, it's easy to see this with a gas, like an engine. When you compress the gas, you got a compression, and that compression, as it moves through here, causes a rarefaction on each side of it, and that wave moves through. So the disturbance moves through this gas. The particles themselves are just go back and forth as this passes through. Instead of the up down here, it's there. Horizontal instead of vertical. And then the surface waves, like in the ocean, if you had a board and you shove this water, you get this rolling effect, and the water actually moves to the right and also makes a transverse pulse to it as well. And this is what the water is doing. So there's a quick summary of the primary wave types.